Thank you everybody for allowing me the opportunity to present here today. I have a bit of a story to tell today. It's a story of two designers. One designer who's designing an ASIC that has an embedded FPGA allowing the ASIC to provide a variety of different accelerations for a variety of different applications. Second person is the FPGA designer. He has the opportunity to develop a variety of different accelerators that go into this ASIC. He's going to get to do his job in a different place and in a different time than the ASIC developer, of course. So, before we get started, what is an embedded FPGA? So I work for Achronix. We've been doing FPGAs for a long time. We have high performance FPGAs. They can be quite large. We have a lot of gates, a lot of lookup tables, a variety of different features. When we talk about an embedded FPGA, we're talking about an FPGA that you can put inside your SoC. So this enables you to provide programmability to your devices, so you can ship one device that has multiple personalities, or to your customers. You can ship this saying that there's an FPGA on board. Dear customers, you have the ability to put whatever you want in here. Typically, we have AXI and A-Slide interfaces. It's an FPGA. The interfaces can be anything you want. AXI and A-Slide tends to be common. And because it's an embedded FPGA and we can do something different for every single device, it's extremely customizable. So you, the SoC designer, get to decide how many lookup tables and how many flops, what's the density of VRAM, LRAM, and DSP blocks, what is the aspect ratio of the LRAM and VRAM blocks, are there any special features that you want in the DSP, and then of course it's your ASIC, so you decide the technology node and the metal stack. We also provide a complete software environment. This is important today because we're going to be talking about timing closure, and timing closure is all about the timing analysis tools. So we provide full Verilog, system Verilog, and VHDL support, full STA support, including OCV derating in multiple corners. We use industry standard SDC files, which is very important and which we'll come back to today. Scripting, built-in logic analyzer, full placement and floor planning support. There's a picture of our floor planning tool. We support simulators, protected and encrypted IP, and we do have partnerships with HLS providers. And then here's a view of our built-in logic analysis tool. Okay, so on to the meat of the presentation, on to the story. So what we have inside of an FPGA is typically, it's predominantly an array of programmable logic, something we call logic tiles. So that's your lookup tables, your flip-flops, and all of your routing resources. Not shown here is the DSP blocks, the memory blocks, etc. On the edge there to the left, we have that green block called a boundary tile. So that's this one right here. Inside the boundary tile, for each input and output, in our SpeedCore embedded FPGAs, we have a bunch of features built into hard logic. So one of the first things you'll notice here is a loopback path. So you can configure the FPGA so that the output from the FPGA cores loop back into the FPGA. This isn't useful particularly in traditional designs, but it's really useful when you're trying to do the ATE testing of your device, when it's coming off the manufacturing line, right? You've got all these loopbacks and you can test all of the different options. You'll note here we also have loopbacks in the opposite direction. We then have bypassable registers, which is one of the key things we'll talk about today, and we have a clock select mux, so you can decide which clock is being used for the input and output registers. Make sense so far? So here we have something I'm referring to as simple timing. Think of this as the introduction to today's story. When we have simple timing, what we've done is enabled these registers. What this means is the ASIC designer, he's thinking about timing closure as beginning in this flop. He's got his output delays, and he goes through his own combinatorial logic, and then he gets to whatever flop is inside the ASIC. The FPGA designer only has to worry about the FPGA logic here, going through the output data path and setting up before this flop. So in this case, these two people, they live in different worlds. They don't really have to talk to each other. We at Achronix provide lib files that provide all of the information you need here for the ASIC designer to close timing. So we give you the output data that you require here. So in this case, ASIC timing is owned completely by the ASIC designer. FPGA timing is owned completely by the FPGA designer. Let's talk about advanced timing. So this is a feature that we've had since the beginning of our embedded FPGA offerings. It's surprisingly simple, but also kind of complex. So this is a mode where we're bypassing this register. So what this means is we have a timing path that starts with a flop inside the FPGA, comes through the boundary tile, and ends up over here in the ASIC. So we have this one timing path that's owned by two different people that importantly are closing timing at different points in time. The ASIC designer, of course, has to finish all of his work long before tape out. The FPGA designer, he doesn't even really get started until the chip's available to play with, right? So We're sharing this timing path that starts inside the FPGA and ends up here outside the ASIC. We have an equal and opposite timing path that starts here outside the ASIC and ends inside the FPGA. The story is a happy ending. It turns out that it's actually pretty easy using the tools that we provide here. So first of all, we provide you with a lib file that represents this IP core, the FPGA, with some representative delays that are representative of a variety of different FPGA designs that you might want to put in there. So we give that to the ASIC designer. The ASIC designer uses that to close timing as a first step. Later on, they collect the information from the ASIC timing closure, all of this data here, and feed it back to our tool suite to our static timing analysis. So the FPGA designer knows how much of the clock cycle he has left to work with. We provide all of these commands with primetime scripts to extract all of the information and feed it back to ACE in familiar SDC timing constraints. One note, the decision between the two is done by the FPGA designer. So you might have one design that's running at a faster frequency where you want the flops along the boundary. You might have a different design that's more latency critical where you're using this advanced timing mode and the flops are deep inside the FPGA. So the timing closure process here is iterative. The ASIC designer chooses the target frequency and determines how much of the clock is going to be used by the ASIC logic. He runs timing closure using whatever his favorite tools are, sorry. So something like primetime. Again, we provide the budgetary lib files. He then extracts the ASIC portion of the delays on each wire and provides them to our ACE tool set via constraint files, and we provide the template and scripts to help generate that. Then the FPGA designer takes over. He's going to take, typically, a suite of example designs, of representative designs that he might want to put into the FPGA. So he might have 10 or 15 different things that he wants to put in there, some compression, some encryption, some machine learning, what have you. Tries to close timing. If he closes timing for all of those designs, he's done, ready to tape out. If not, then one of two things has to happen. Either the FPGA designer agrees that he's going to change his FPGA designs to have less logic before that first flop, or the ASIC designer goes back and changes the ASIC design to give the FPGA designer more of the clock cycle later on. So, the ASIC integrator, again, uses industry standard files and the lib files that we provide. If I have an example advanced timing mode here where the clock source is in the ASIC and then it's being driven into the FPGA here, the ASIC designer obviously has to worry about clock delays TC1, TC2, and then TC3, 6, and 4, and 5. Data delays, he's concerned about 1, 2, 5, and 6. So we scrape all of that information from the ASIC timing closure process and provide it to ACE. Oops. The FPGA designer gets that information and feeds it to the ACE tool set as a bunch of SDC constraints. So this looks familiar to anybody that does ASIC SDC constraints. It's just something that we feed to our FPGA tool. And you can see what we're doing here is taking some derating factor, some derating number, my words aren't coming to me, some derating factor, and we're going to take the delays for rising and falling edges for all of these clocks that are outside the FPGA core. Then we look at rising, falling, late and early conditions, so you've got your best and worst case PBT variation. We figure out what the worst one is, we add the clock and the data delays together. We add a little bit of we add a little bit here for clock pessimism recovery. That's it, clock pessimism recovery. And then we provide it to ACE using a familiar set input delay constraint. Okay, so really easy stuff. Here's another example of what we can do. In this case, the clock source is outside the FPGA core, and the FPGA designer is able to decide which of the various clock sources that they're using by specifying it inside the FPGA design. It's very similar flow. The ASIC integrator is going to treat this as a clock in his system. He goes and closes timing using the same delay elements that I talked about on the previous slide. All of this information gets collected up into SDC files for the FPGA designer again. The FPGA designer, he can now choose which clock he's going to use at FPGA design time, and it just flows through. The ACE tool correctly handles the fact that this pin here is now an output pin based on the clock source, as opposed to the input pin it was in the last cycle. So I've shown two modes here, because I only have 12 minutes to present, but we can actually support a variety of different modes. We have a variety of different clock inputs. We have region clocks, we have core clocks, we have something we call mini trunks. So there's a lot of variety here and a lot of possibilities. Okay, so to summarize, with embedded FPGAs, clock paths can be shared across time and space They go left and right across this line, but they're also shared in terms of the development time. The selection of advanced versus simple timing mode is done by the FPGA designer, so before you tape out, you want to make sure that you close timing with both modes. The ASIC designer uses standard static timing analysis tools, so there's nothing new, nothing scary. It's something that's very familiar to him or her. And the FPGA designer also uses the industry standard SDC file format, but feeds it to the Achronix static timing analysis tool to close timing for the FPGA. Okay, thanks everybody.